in my opinion, a very interesting and very different topic in the OT cybersecurity domain. Typically, when we talk about OT security, we focus on just the firewalls and the intrusion detection system and the SIEM and the SOC, but we forget about the PLCs or the controllers themselves, which ultimately are the sort of the key components that we are trying to protect when it comes to cybersecurity. So today I thought we'll talk just about a little bit about how the different programming techniques in the PLCs they impact cybersecurity. Before we proceed, Maimuna, can you throw the questions on the screen? And while Maimuna does that, I like to get to know my audience a little bit because it helps me tailor tweak my presentation to the background of the audience. So the first question is on the screen. Please respond to it. Which of these domains is the closest to your primary job function or primary area of expertise? It's control systems, OT cybersecurity, IT security, just IT infrastructure, or others. I'd appreciate if everybody can give the answer so we can proceed to the next question. So I see that a lot of folks are from the OT, either control systems background or OT cybersecurity, which is good. So maybe I can skip a few concepts within the presentation. Thanks, Maimuna. Let's move to the next one, please. All right, the next question is, have you ever programmed a PLC or configured an HMI to communicate with the PLC? And obviously, I'm sure the control systems folks, they have done that, but some of the IT folks may not have done that. But if you have any exposure to this, please share it with us. All right, so as expected, significant number of attendees, they have done the programming themselves, but there are a few who haven't, so I'll make sure that I take everybody together. I don't want to leave anybody behind. Next question, please, quickly. All right, so have you ever considered cybersecurity implications when developing a PLC program or application or logic? If you have programmed the PLC, if you haven't done it, just say no, you haven't done it. But if you have, do you think about it when you're programming the logic? Do you think about how your programming technique can impact cybersecurity? Nice, very nice. So a few folks have done that, maybe a quarter if you have thought about cybersecurity when programming the PLCs, but most haven't. So that's good because that's the topic of today's discussion. So with that, I'll move on. Very quick introduction. My name is Mubarak Mustafa. I'm a senior consultant with over 30 years of experience in industrial automation and control systems, and then OT cybersecurity, programming PLCs, HMIs, DCS, SCADA systems. That's what I've done in the, I guess, significant part of my career, and a few credentials to go along with it. I'll quickly move to this part. I'll skip these slides. I put them in the beginning for every, I guess, presentation, but it's not relevant. Most of you understand what control systems are. You've seen the industrial plants where you have some operators controlling the plant, but there is a very complex control system architecture in the back with a lot of devices, networks, components, and all. So I'll skip through these in the interest of time and quickly move on to the topic at hand today. So let's talk about these control systems components and how PLC programs they work. And because some of folks, or maybe half of them, they have not done PLC programming themselves, so I'll quickly try to sort of spend maybe 5-7 minutes on how the programming and HMI communication works. So it's the same picture that you saw a couple of slides ago, a complex network architecture that has a lot of, you can see, PLCs or controllers I'm using the term PLC in general, and I want to sort of state that focus will be on the PLC. Obviously, there are different type of control systems. There are DCSs, and then there are some specialized control systems as well. But I want to keep it generic for the just for the sake of everybody's understanding of the concept, the core concept we are talking about, which will apply to all of different types of control systems. So in a complex environment, you may have hundreds of such controllers or PLCs or control devices in a facility, and lots of networks and the HMIs and engineering workstations and all controlling a big refinery or a petrochemical complex or something like that. But if I try to simplify it to take I guess the complexity out of it, in a nutshell, these are the three main components of a control system architecture. There are a lot more, so I know there are historians and then the data servers and all those things. But simply put, you would have a PLC or some kind of controller. You would definitely have some kind of a network so the PLC can connect to different devices. You would have an engineering workstation, which we will see what the purpose of the engineering workstation is. And you would have something called an HMI, human machine interface. Together, this is basically the gist of any control system. And on the bottom, I have made a simplified industrial plant. Of course, this is not really an industrial plant, but uh, it is uh, it is simple enough for us to understand the concept that we are going to discuss today. So I'll start with this so-called industrial plant. It's simply a water tank which can store water. Water can get in from the top, from the inlet, and there is an outlet on the bottom for the water to go out. There is a level transmitter over here, a device that can sense what the level of water is within the tank. You can forget about this solenoid valve for now for today's discussion to keep it simple. But I'm sure everybody understands what a pump is. A pump can pump water from one side to the other. So in a nutshell, there's a water intake. This pump, when it's running, it will send the water to the tank, and the tank will get filled with water, right? And I'm sure there is some water consumption on the bottom, which we will assume that water is being consumed, and the tank level will go down as more water is consumed. So in this sort of very complex plant process, our goal is to keep the water in the tank at a reasonable level so that when any kind of process downstream needs the water, there is water available in the tank. So that's our industrial process. Now, now that we're done with that part, let's look at a little bit on these three key components of the control system and understand what the role of each component is within the control system environment. And I'll talk strictly from cybersecurity perspective. So on the bottom, you have the PLC. The job of the PLC is to interact with the industrial equipment, with the pump, with the valves, with the sensors, to sense or monitor what is going on in the industrial facility or the equipment, and to initiate controls, maybe starting and stopping the pump, opening and closing a valve, or thousands of similar operations that can be performed. So that basically is the job of the PLC. And it's important to understand that because at the end of the day, when we talk about cybersecurity, we know that in industrial control systems or OT cybersecurity, the so-called the triad that we have regarding confidentiality, integrity, and availability is kind of flipped. Confidentiality is not as important. The biggest concern is availability. You want to keep the plant running, and you want to make sure that it keeps running the way it's supposed to run. And guess what? Which component is actually running the plant is this PLC or similar PLCs or controllers that you may have. So if you want to keep the plant running and you want to keep it running safely and the way it is supposed to run, then then ultimately you need to protect the PLC. So while there are a lot of other network components or control systems components on the top, the HMI engineering workstation, we'll talk about that. It could be historian or application servers or advanced controls and all those things. But ultimately, if the PLC is compromised, then that's where basically your biggest risk is to the safe and reliable operation of your industrial facility. So that's what the PLC does. Some of the characteristics of the PLC relevant to the topic today. It has proprietary operating system as opposed to some of the computers that we use, even on the HMI and engineering workstation, Windows or Linux, that's about it. You're not going to get anything else. You may have different versions of Windows, but that's it. On the PLCs, it depends on the manufacturer. Every manufacturer would have their own proprietary operating system. Maybe underlying could be Unix or Linux, but they would have built something on top of that, which means that it's not just generic Windows that can be with the risks and benefits of a typical Windows or computer environment. Another important thing to understand that in most PLCs, and I'm talking about legacy, so there are exceptions, especially the newer PLCs and controllers, they have a lot more cybersecurity features, but bulk of the PLCs installed around the world, they have limited or no authentication for program transfers from the engineering workstation. So when the engineering workstation communicates with the PLC to transfer the program, or the way we like to call it, download the program, there is usually limited authentication. Some PLCs may have it, but in a lot of cases, there is no username and password. There is no authentication as to who is downloading the software and whether it is authorized or not. As long as the appropriate configuration software is used, you can download program. I can bring my own laptop, connect it over here, run the programming software, connect it to the IP address, and download a new program altogether. So just remember this, that limited or no authentication for program transfers from the engineering workstation. Similarly, and we'll talk about the HMI PLC communication also, most PLCs support several communication protocols for data exchange. While the programming part is proprietary, the data communication part is usually quite open. You would have, there are several communication protocols, Modbus TCP, Profibus, Ethernet IP, or DNP3, and all. There's a long list of that. So they are more open source or more general purpose communication protocols that can be used to exchange data from the PLC. And we will look at the difference between program and the data. But the important point to remember is that even when it comes to data exchange, there is again limited or no authentication in the PLC. So anybody who would know what data is available in the PLC, they can request either to read the data or write to the data variables in the PLC without any kind of restriction. Let's talk about the engineering workstation. What is the role of engineering workstation, or EWS in short, in this whole scheme? The EWS is used to create or modify the PLC programs or the PLC application, or some people like to call it logic because it's a programmable logic controller. But this is basically your engineer sits and programs what kind of function the PLC must perform. The programming is also done using proprietary software. The program is developed on this EWS and saved on the local hard disk over here, compiled, and then the compiled version is downloaded or transferred to the PLC. So you can see that even that transfer protocol is proprietary. Everything that we are discussing up until now is all proprietary. The engineering software up here, the communication protocol, and the format in which the program or the application logic is transferred. All of that is proprietary to that particular OEM. So if it's Rockwell or Siemens or GE or whatever, it's going to be for each one of them would be different. Now, when it comes to the HMI or human machine interface, that's even more simple. The job of an HMI is to read and display data from the PLC. That's it. Read data and display it on the PLC and the tank and all those things. And if the operator sitting over here wants to take an action like start the pump, stop the pump, the operator will click on like an icon on the screen, and the HMI will send that command or that data element to the PLC, and that's about it. The HMI cannot change the PLC program. It can only modify the data, the variables inside the PLC. And last but not the least, any software can act as an HMI. This is a big difference from the EWS. In case of EWS, only the proprietary software from the PLC manufacturer can be used to develop the program and to download it. But in case of HMI, I can literally read data into Excel. I can put a computer over here with Excel, or there are tons of general purpose software in the available on the internet. I can install that, connect it to the network. As long as I have the driver, communication driver for the protocol that the PLC supports, I can read data, I can write data to the PLC. So what we have done over the past few minutes is to understand the key components in this whole architecture, and we'll focus on the same screen when we try to elaborate the point about the programming technique. So let's see what a PLC program and HMI communication looks like. What I've done over here is I've written a very simple PLC logic, PLC application, or PLC program, whatever you want to call it, for this very, very complex industrial plant. Now, what this program is saying is when the level in the tank, when the level transmitter is sending a value, that the level in the tank is this much. When the level is less than 20%, then send a pump command, make it 1, which will start the pump. So as soon as the level goes below 20%, the level transmitter is sending the value. This logic will compare it is less than 20%, make the pump command 1, so the pump gets started. Similarly, if the level is above 80%, is it above 80%? Yes. Make the pump command 0, so the pump stops. Very, very complex logic, right? Well, it's as complex as the industrial facility that we have down here. So what this program will do is that it'll keep the level in this tank between 20% and 80%. It goes below 80, the pump starts, it goes up. It crosses 80%, the pump stops, it goes down. So between 20% and 80%, it's going to fluctuate. Nothing wrong with this program, but let's see what happens next. Obviously, the job of the engineering workstation or the control system engineer, which a lot of you may be, the job is to write this program, click on the few buttons on the screen to compile it and download the program to the PLC. Okay. Once the program is downloaded to the PLC or transferred to the PLC, the job of engineering workstation is done. You can turn it off and that's it. Nothing's going to happen. What the PLC will keep doing is it has a copy of the compiled version. It will continue to run this program forever as long as it is powered up. It will keep reading the level, keep checking. If the level is above 80%, stop the pump. If it is less than 20%, start the pump. So this is our beautiful logic that we have created. The PLC also has something called the memory, where these values are stored. This is the program, and this is the variables or the tags, sometimes people call them, where the values are stored. So when the level transmitter is showing 20%, the PLC will have 20 in this variable. The pump is running, so the command would be 1, and maybe there's a pump feedback that is saying that the pump is also running. And all this data is transferred to the HMI. The HMI can read these variables or values and show it on the screen. So that's basically pretty much how the control systems work. You do the programming, you download it to the PLC continues to execute the program, it continues to update its memory variables, and those variables are read by the HMI and displayed on the screen. Now, the problem with this program is it's a very nice program. It'll make sure that the level in the tank stays between 20 and 80. But one fine day, the plant manager comes in and says that I think we have a different need for water today. If we let, there's going to be a lot of users. So if we let the water go to 20, even you start the pump, it will not be sufficient to keep the supply going. So I want the pump to start at 40%. As soon as the level goes below 40, I want to start the pump. Now, guess what? This number 20 is hard coded in the PLC. You have to call the control system engineer who will have to modify the program in the PLC programming software on engineering workstation, and he or she will have to change it to 40 and then again download the program to the PLC. This downloading thing sometimes, not always, may even require you to shut down the facility. Some PLCs, they don't allow you to download the program while the PLC is running, so they may temporarily stop operating while you're downloading the program. So just because you wanted to change your sort of set point from 20 to 40, you had to shut down the facility. It doesn't make any sense. So while this is a perfectly workable program that we have up here, it's not very suitable for good plant operation, especially the operations folks who need to continuously tweak the plant's operation based on different parameters. They're not going to like it. They want to be able to sit over here on this screen, click on a button, and move it from 20 to 40, and then that data gets transferred over here. That's what they would want to do. And that would make the pump start at 40% instead of 20%. So to make this a better operational, improved operation, I slightly tweaked the program now. I'm not talking about cybersecurity yet. I'm saying improved plant operation. Instead of hard coding the 20% here and hard coding 80% over here, I have used two variables or tags called LSP low set point and HSP high set point. LSP referring to this part and HSP referring to this part. Now that these two have become variables, I have this option that I can put in any value in these two variables and the PLC will act accordingly. So if I put 40% over here and 80% over here, my beautiful logic will make sure that the level in the tank stays between 40 and 80. And one fine day, the operators say, no, today we want to make it 30 to 70 for whatever good reason that they have. As long as I change the value of these variables, the level in the tank will stay between 30 and 70. So now what we have done is we have improved the operational part of the PLC program. It is much more better usable. You don't need to modify the program. You can keep this engineering workstation shut down, and you can continue to operate the plant as long as this logic is all you want. In addition, what we have done here is that in addition to reading these values on the HMI, we have put some boxes over here called LSP and HSP. And as soon as operator clicks over here, whatever number they enter here, that number gets communicated to the PLC. Remember, we talked about that the HMI only changes the data in the PLC. The HMI cannot change the program, but it can change the value of these different variables that we have in the PLC. So while we have improved the overall functionality of the program or usability of the program, we have also introduced at this time flexibility for the operators to be able to operate the plant whichever way they want by simply just clicking on a couple of buttons and entering the value 20, 30, 40, 50, whatever they would like. So this basically clears up the scope of PLC and I'm sorry, the engineering workstation and the HMI. Anytime you would like the program to be changed, you need the engineering workstation. You need just the data to be changed, you can do it from the HMI. Now comes the interesting part. Remember I talked about in the previous screen a couple of things regarding the PLC and the HMI. I'll go back to those screens here. PLC doesn't have any kind of authentication for data exchange. And PLCs support several communication protocols for this data exchange. HMI is just a general purpose software. It doesn't have to be the same company as the PLC. Like I said, I could use Excel to do this or some other generic software to send data to the PLC. Now let's combine these two things. I can send data to the PLC without any kind of authentication mechanism. All right. What that means is that if I put a computer over here, a hacker computer, and I install a general purpose, again, I'm using the word Excel, but you can install any kind of software here, which can download those values to the PLC without any kind of authentication, you can quite significantly mess up your operation of your facility. So what can happen? Let's look at that. Go back over here into my beautiful upgraded application with the variables. What happens if I put 80% over here? The pump will stop at 80. What if I put 95% over here? The pump will stop at 95. What if I put 105% here? The PLC will check if the level greater than 105. No, because the level will never go above 100% in terms of the reading. So what will happen, the pump will keep running and your tank will overflow. Whatever is in the tank, I'm talking about water, which is okay if the water overflows, but if it's a hazardous liquid or some kind of hydrocarbon, some oil and gas, it's gonna overflow. So that's basically the so-called hazardous condition that is being created because now we are writing an unauthorized or a value that doesn't suit the overall plant operation. Based on this PLC program, what I just explained is very much possible because any HMI, whether it is this one that is on the screen or somebody pretending to be an HMI, can write this value to the PLC, and there is nothing the PLC can do about it based on this particular program that we have. All right. So now we have improved the plant operation, but we have created a cybersecurity headache because, a hacker or attacker or whatever that is can simply write an invalid value to a PLC variable, very simple, using off-the-shelf communication protocols and software, and it's going to mess up my beautiful industrial facility. So in this scenario, for this particular plant, let's talk about what the different attack scenarios can be in this case. There's a PLC, there's an engineering workstation, there's an HMI. What are the different cyber attack scenarios that can happen that can compromise the PLC or negatively impact the industrial facility? An attacker may infect the PLC itself. That's a possibility. The attacker may directly attack the PLC and change the parameters, like getting inside the PLC directly and changing something in the, I guess, the operating system. The operating system part is over here, attacking the operating system of the PLC. But this direct attack is getting inside the PLC and changing the parameters or even the PLC program. That's also theoretically a possibility. attack the engineering workstation or pretend to be an engineering workstation and create, modify, or download a compromised program to the PLC. That's also possible. Or the attacker may attack the HMI or pretend to be an HMI and send wrong data to the PLC, just like we saw in the previous slide. So these are some of the, I guess there could be more, but uh, focusing on the core, these are the 4 core scenarios that can happen that can compromise the PLC. In terms of the level of difficulty, it's the most difficult is on the top. Because remember, PLC operating systems are proprietary. It's not like Windows that has, so many vulnerabilities because it has Internet Explorer or Microsoft Edge. It has to go to the websites and all those. Nothing. PLC is a very closed proprietary type operating system. So infecting the PLC itself, creating a virus that runs inside the PLC, while theoretically possible, is very difficult and unlikely for a typical average industrial facility. And I'm not talking about state actors and those things. I'm talking about a typical average industrial facility that doesn't have a threat from, let's say, very advanced attackers. The second one is still quite difficult. Okay, getting inside the PLC and changing the program within the PLC is very difficult. Maybe slightly less than the first one, but still, I would say quite difficult. Attacking the engineering workstation or pretending to be the engineering workstation and downloading a compromised program, that's actually relatively easier than the first two, but still quite hard. And if somebody wants to really study about it, this is where the good old famous Stuxnet did this. Even Stuxnet didn't go over here or go over here. Okay. You can read about it, but this is basically even Stuxnet was at this level, and that was a very advanced virus. The most simple and easiest one is down here. Anybody who has basic understanding of PLCs and control systems can create a malware, a virus that can sit on the network and send wrong data to the PLC. I actually created like for our lab internally, not a real virus, but in a lab in a test environment. It had about 20 lines of code, and it would write a certain value to Modbus TCP addresses in the PLC, and it worked. I would plug in just a USB, plug in a USB to any computer on the network, and it would write incorrect value or send incorrect data to the PLC. So this is the easiest part. So while we need to have protection against all different types of threats, in my opinion, as a minimum, we need to focus on this part. Because while these are also possible in terms of risk, because risk is based on probability and impact, the probability of these first 3 happening to an average industrial facility is quite low. Probability of this happening is, in my opinion, a lot higher than the first 3. So the higher the probability, the higher the risk. So this is what we need to protect, in my opinion. And that's basically what we are talking about today. So I'll just reiterate the same 4 parts over here, that if there is an attacker, and obviously whoever the attacker or threat is, they need to have access to the network. If they're sitting over here, can they go inside the PLC and modify the operating system? Yeah, but no. Can they go inside the PLC and change the program within the PLC? Yeah, I would like to see that. But can they infect the engineering workstation, modify the program here and make it 0, for example, and then download? Possibly, but still quite advanced. They can even act as the engineering software themselves and download the program. That's also possible. But again, we're talking about the high probability items. But the last one over here, that somebody infecting this HMI or sitting on the network pretending to be HMI and just writing 105 on this memory address, that's easy peasy. So how do we protect ourselves from this kind of easy peasy attack scenario? Yeah. Well, first of all, we need to look at over here. This is the core message of the discussion today, that not just from security perspective, but even operational perspective, you don't want an operator to, by mistake, enter 105 here, HSP, entering 105 and sending that data to the PLC, and then your water tank overflowing. You don't want that. So even from operational reasons, you need to have this kind of programming practice, but especially from cybersecurity perspective. So just to give you an idea, I have modified the program and including some cybersecurity considerations in the program. So it's the same program. It does the same thing, nothing more than the 20 to 80% maintaining the tank level. But what it does is that before it goes into starting and stopping the pump, there is a hard-coded limit, and this will be done by whoever is responsible, the engineers who are responsible for designing the facility. If they don't want that the set point ever goes above, my mistake over here, this should be high set point. If they don't want the set point to go above 80, they can hard code that the operator has the flexibility to enter 75 or 70 or 65, whatever they want, but it can never go above 80. Similarly, for low set point, they can enter 30 or 25, but they cannot enter 19. This is what this particular part of the logic will do. So anytime somebody tries to write a value of less than 20% to this low set point, the PLC will cap it at 20%. And if someone tries to write a high set point value more than 80%, the PLC will cap it at 80. So this is just a very simple example of what you can do to ensure that whatever your peak limit, max limit is, nobody can by mistake or intentionally an attacker cannot change the value beyond the cap that we have. Now, if you have the program down here, same program that we had before, now it'll be okay. In this particular case, your level will never go above 80 and it's not going to go below 20. No matter what the HMI writes to these tags, these variables, or no matter who is sitting over here trying to mess with your facility. No, the low set point will never go below 20% and the high set point will never go above 80%. This is just one example. Within the 20 and 80, the operator is free to choose whatever value is suitable for the plant operation. Similarly, I've added another sort of check over here that in the previous logic, if the level was between 20 and 80, an attacker could still stop the pump or start the pump because the logic is only checking when the level goes below 20, it'll start the pump. If it goes above 80, it'll stop the pump. But in between, the logic was not doing anything. So an attacker or hacker or the operator by mistake could still write 0 or 1 to the pump command and start or stop the pump. Now, what I've done is that I've added another command over here, another line over here, that in between 20 and 80% of whatever the low set point or high set point is, keep the pump in the last state. If it was running, make sure it keeps running. If it was off, make sure it stays off. So these are slight small improvements in the PLC program that can be done to prevent unauthorized or unintended data to be written to the PLC variables and resulting in unintended operation. So in a nutshell, if I look at this coming back over here, what we have done is that on this last part of it, this attack, that somebody who attacks the HMI or pretends to be an HMI, sending wrong data to the PLC variables, which would result in unintended operation in the facility. Uh, by changing the PLC programming technique, we have addressed that. There are other things that can be done because a lot of time we get that question. There are other things that can also be done to protect from these kind of attacks as well. I'll briefly touch on that because even though that's not the topic today, the topic was mainly focusing on the way you program the PLC. But you could still, for instance, if I put, it's a very, I guess, aggressive thing to do, but if it's a critical PLC, if I put a firewall right above the PLC and say that only the engineering workstation is allowed to download the program and only the HMI is allowed to download or send the data, that will basically take this third thing out of the equation. So if there is another device that is on the network that is trying to communicate with the PLC, whether pretending to be the engineering workstation or pretending to be an HMI, would not be able to download the program or send data to the PLC. But putting a firewall um, at every PLC is something that is not feasible practical. If you have hundreds of PLCs in a facility, you're not going to install firewalls in each of these PLCs. And obviously, every time you introduce firewall, it may add further, I guess, either the lag in communication, or if nothing else, it adds another point of failure. If the firewall fails, then the communication is gone. Well, now you need to put a redundant firewall, and that becomes a different ballgame. But keep in mind that if you install the firewall over here, it still doesn't prevent somebody who has infected the HMI itself. It doesn't prevent them from writing the incorrect data to the PLC, because in the firewall, you have allowed that HMI can talk to the PLC over Modbus TCP, for instance, that this HMI can talk to this PLC over Modbus TCP. So if there is a virus on this HMI, or if this HMI is compromised itself, whether through remote access or whatever other different ways that can be compromised, then the compromise mechanism, whatever that is, can still write incorrect data to the PLC. So just this part, installing a firewall, is not a full resolution to protecting the PLC. You will still need to modify the application to make sure that even if someone tries to write or send incorrect data to the PLC ignores it or doesn't use it. Same thing with the engineering workstation. Even if I put the firewall down here, that will allow only the engineering workstation to download or transfer the program to the PLC. That would mean that a third device or even an HMI, compromised HMI, somebody's trying to install the engineering software over here and trying to download the program from here. Well, that's not going to work because the firewall will prevent it. So there are several other external security controls you can put in place to protect from some of these advanced attacks. But in my opinion, you should take care of this one because this is the easiest form of attack. And if your PLC program is not programmed, PLC application logic is not programmed appropriately, then this introduces significant risk to your facility. So here's the conclusion. Unauthorized data write to PLC variables is the easiest way due to limited protections in most PLCs. Like I said, there is no password or authentication. Any device on the network can write as long as they have the communication driver for the communication protocol, they can write data to the PLC. External security controls should be implemented to limit access to the PLCs. Just like we said that maybe you should install a firewall, not for all PLCs, but at least for the critical ones, or depending upon where appropriate on the network, you should implement those security controls to limit access to the PLCs themselves. Because remember, PLCs are not very, security friendly. You should have improved programming techniques, but keep in mind that the improved programming techniques that I just gave example about, they cannot prevent the attack from occurring. So if somebody is sitting on the network and trying to send 105% or 105% to the high set point, the programming technique itself cannot stop the the data communication, but it can minimize the impact of such attack. So if you have put in that limit that we talked about, the program, the PLC will still receive the value of 105%, but it will ignore it and cap it to 80 and make sure that it doesn't go above 80. I do recommend that for new projects, adopt good programming best practices, just like I gave very simple example. But think of cybersecurity when you're doing the PLC programming or designing the PLCs. Think of how you can, what programming controls you can put in place to minimize the unauthorized data modification or to minimize the impact of unauthorized data modification to the PLCs. For existing or legacy PLCs, extremely difficult. You're not going to go in, and there are like millions and millions of PLCs out there installed for the past 30, 40, 50 years. There's no way anybody's going in and modifying all the logic to make it security compliant or implement security best practices. But you may want to modify some critical PLCs in your facilities. If you have a particular PLC which is the most critical, and you see that that particular parameter high set point is something that I don't want this to be ever compromised, then maybe change that particular parameter or put extra checks and balances within the program to make sure that it provides improved protection from such threats. All right, so that's about it. Time for some questions. Let me see if I have access to the questions. Let's see, how can I go back here and stop sharing? All right, so if you have any questions, please feel free to post it on the Q&A. You have a Q&A button on your screen with a question mark. Feel free to post your questions so I can address those. So there is one question about risk assessment and control system programming. I think I indirectly addressed it. This is exactly what you should do. When you're programming the PLC, you cannot put such controls, even though the controls that I gave the examples about, they're quite simple. You're just capping the low set point and high set point. But if you start putting such caps on everything, it becomes the PLC program application becomes too big, too complex. You have maybe 100 lines of actual logic and 1,000 lines of protection. It's going to just slow down the PLC, or it may have other negative implications for you. My suggestion is that you look at the process. At the end of the day, it's all about, let's say the example that I gave was really a water tank. Yeah, you don't want the water to overflow, but if it does overflow, what's the big deal? Well, it depends on where it is. If it is just somewhere in the desert, and if it overflows, it's nice, it's okay, then you don't need to worry about it. But you do your risk assessment for the equipment that is being controlled, the parameters that are being controlled, and then decide what level of protections you want to put in in the PLC. Any specific standards to be followed in the programming? That's a tough one. ISA, the International Society of Automation, they do have some guidelines about how to program the PLCs, but I don't know, frankly. There may be out there. I don't know if a particular standard specifically for from cybersecurity perspective, whether it can improve the cybersecurity of the program or not. All right. Another question is that differentiate between secure and safe PLC programming. Very good question. Thank you very much. They're kind of interrelated. At the end of the day, when I started the presentation, I talked about the job of the control system or the PLC is to keep the plant or the facility running the way it is supposed to, and safety is the most important part of that. You don't want the safety to be compromised and have any kind of a negative impact like an explosion or equipment damage or anything like that. Safety in PLCs and control system has been it's a mature topic. The industry has been working on this for like decades and decades, maybe 50 plus years. So there are programming practices for safe programming of the PLCs, but I'm talking about secure. I mentioned a little bit, I think I implied about it, that the improved program that I proposed, it not only protects you from cyber threats, but it also protects you from unintended, like the operator sitting at the HMI by mistake types an incorrect value that creates an unsafe situation in the plant, in the facility. Obviously, that is part of it. So when you implement these best programming practices, it will definitely help you from safety perspective as well. It just so happens that safety is already well, I guess, ingrained in a lot of, in I would not say a lot, in most industrial facilities, but security is usually overlooked. So I wanted to emphasize the security part of this. Point one is covered. What was the point two? Yeah, we talked about the standard part, and that is also covered. What else? Can firewalls prevent? Yeah. So there's a question about firewalls. Can firewalls prevent unauthorized access to the PLC? I think we covered that quite a bit. Maybe the question was posted before that. Firewalls can prevent unauthorized access for sure, from unauthorized devices. If the firewall is placed at an appropriate point and properly configured, then it would prevent unauthorized access from unauthorized devices. But if if the HMI itself or the engineering workstation itself is compromised, then it will be very difficult for someone for the firewall to stop it, because the firewall is supposed to allow communication from the HMI to the PLC on Modbus TCP. So if the same HMI or some other software on that HMI is trying to download or send an incorrect value to the PLC, it will be very difficult to stop. The firewall cannot stop that. We're running out of time, so I'll just take maybe one more question or point. There's a point about there could be multiple PLCs communicating with each other. Absolutely. I tried to keep things simple. I gave the example of HMI communicating with the PLC, but in a typical plant, you would have hundreds of these controllers and PLCs and other control devices, and a lot of them may be communicating with each other. So it's not just that the HMI is sending data or set points to the PLC. There could be other PLCs talking to the PLC. So if you implement these best practices for programming in each PLC, you would basically cover for all of the communication, whether it is coming from the HMI or from other PLCs or from any unauthorized device. It doesn't matter. So yeah, in case of multiple PLCs, you would have the same best practices. It says fundamentals like input validation and proper documentation are important in control system programming. What other foundational areas should? Okay, I think that's a general guidance question. I'd be happy to provide guidance separately out of this webinar. But I think that's about it. We're out of time. Thank you very much for your participation and very good questions. Hopefully you benefited from this webinar. I'll go back to my screen and quickly show you the next one that is upcoming in January. This one will be on the topic of OT cybersecurity for engineers, what control engineers should know today. A lot of us are coming from control systems background. Cybersecurity was never our best, I guess, focus area, but because it is becoming extremely critical for control systems to be secure, it is important for the control engineers to learn about cybersecurity. So it's going to be on 29th of January. You can scan the QR code and register for it. Thank you very much. Back to you, Sam.
Well, thank you very much, Mubarak, for the informative webinar. Thank you so much. And thank you everyone for joining us. Hope to see you again very soon, inshallah.